One very important constraint inside a CP solver is the sum constraint. You will use this constraint in most of your models, and it also contains some good examples of trade-offs between efficiency and filtering, and also some interesting algorithmic ideas that you can put and you can reuse in many different situations inside other constraints. So the domain consistency for some constraints, which means removing all the impossible values from the domains, is a NP-hard problem. Okay, you have a straightforward reduction to the subset sum problem, which means that it's NP-hard. So you surely do not want to solve an NP-hard problem at every node of the search tree, because that would be too costly, and the search tree itself is potentially exponential, so you don't want to do that. Usually, you always want to keep the time complexity of your filtering algorithm polynomial time. So we need to do something else, okay? And it's always a trade-off between a strong filtering but that is slow and a weak filtering that is fast, okay? It's always a trade-off. And there is no easy answer to guess which one is the best choice, okay? Because the size of the search tree will be impacted by this choice. If you have a strong filtering, you will have a smaller search tree. And if you have the weak filtering, you will have a larger search tree. But if you do the multiplication of the size of the search tree times the time that you spend in each node, okay, it's not clear which one is the winner of this, okay? And so usually it's more an experimental decision. You just experiment with some instances of your model, and then you try to tune which is the best choice in terms of filtering strength for your model, for solving your model. So it's hard to predict. So I like to show the difference between domain consistency and bound consistency, which are two different levels of consistency, with a binary constraint. So it's a binary constraint here between the variable x and the variable y, and the green region corresponds to the feasible combination of x and y. Okay. The domain consistency will do exactly this. It will project the green region on the domain of x and the domain of y. It will project it, and then it will filter out the blue part. Okay, this one should be removed from the domain. This is too costly to do for the sum constraint. So instead, for the sum constraint, we'll do a relaxed form of consistency, and we will prevent the creation of holes inside the domains of the variables, and so we will project the minimum and the maximum of the feasible regions, okay, like this, okay? And so this is the part of the domain that you will remove. So clearly this is a relaxed filtering compared to that one, but we can do this one much more efficiently for some constraints, and the sum constraint is one example. So let's take an example of the sum constraint and see what we can do in terms of pruning. We have here x1, x2, x3, and we want the sum of the three variables to be equal to 0. And I would like to do the filtering for the domain of x1. And so I will put x1 to the right here. So it will be, the domain will be minus 100 up to 10. Okay. And you have a minus here. So it's minus 10 to 100. And you have the addition of x2 plus x3 here on the left. If you do the addition of the two ranges, you have this and you have this. Okay. And so you have an equal sign there, so you want them to be equal. So you take the maximum of the two minimum and the minimum of the two maximum, which consists in the intersection of the domains. And so you can update the domain of x1 to this, okay? And you didn't create any holes here. So clearly, doing this you can do it quite efficiently, this kind of reasoning inside an algorithm. So the consistency check of the constraint will simply do the addition of all the minimum of the variables, all the maximum. And if 0 is between the sum of the minimum and the sum of the maximum, then you can say that there is at least one solution to the sum constraint if you consider that all the domains are ranges. The filtering can be done in linear time for each variable, because the maximum is simply the sum of the minimum of the other variables. Okay, and you put an opposite sign in front of it. Okay, and you can do that for every variable. And you have a similar reasoning for updating the minimum, of course, of the domains. So if you need to do it for all the variables, you could say that it would require you n square time complexity to do the filtering for all the variables for some constraint that contains n variables. Can we do better than this? Because n square is already quite costly, especially when you have a large number of variables. And the idea is, yes, we can do it more efficiently by pre-computing the sum of the minimum and the sum of the maximum. I will call this S-min and S-max. Okay? And so the consistency check is checking that 0 belongs to the range S-min, S-max. And for the filtering, you can do it once you have computed the sum of the minimum and the maximum. You can do it in constant time per variable. Okay? You can simply use this rule. You take minus the sum of S-max plus Xi max, which means that you cancel the contribution of Xi max to S-max. This is exactly what we wanted to do in this rule. You see that in this rule, we don't want to take the summation of the variable I itself. We want to cancel it. And this is what we do here. Okay? We cancel the contribution of the variable I in constant time once we have pre-computed the sum of the minimum and the sum of the maximum. And so since this can be done in order of 1, this can be done in order of n. If you want to apply it for all the variables, it will be order of n for filtering all the variables. So this is a clear improvement over the naive algorithm that will do the sum for each variables. Can we improve even further the time complexity of the sum constraint and make it incremental? And this is also a fundamental concept when you want to implement the constraint. You do not want to start from scratch the computation. You can do it incrementally, update some data structure. And this is what we will do as we dive in the third tree. We will compute the sum of the variables that are fixed, and we will keep in a separate set the set of variables that are not yet fixed, that are not yet bound, because these are the only ones that I have a chance to prune. Okay? And so I need a way to store the sum of all the bound variables and to store which variables are not yet bound. And to do that, I can use my state management object like the state sparset and the state integer. So let's see in details what we can do. Assume that I have 6 variables. Okay, initially none of them is fixed, and so the partial sum is 0. And this is my pruning rule. Okay, S-min will be the sum of the bound variables plus the sum of the unbound variables. Okay, and sum is a state integer that will store the sum of the bound variables. So if I take a branching decision like x0 equal to 4, my sum should be augmented by 4, and you see that the variable 0 here has been removed. If I now assign x5, I say it's different from 2, nothing changes here, and the sum is still 4, because there is no change in terms of unbound variable. If you go to the left, you will probably assign the variable, x5 in this case, and so it should be removed from the set of unbound variable, and the partial sum has been augmented by 1. Okay, so now it's 5. Okay, and so you really augment it gradually, these two states, the partial sum of the bound variables and the set of unbound variables. And once you have them, you can prune the variable more efficiently. Okay, you continue like this. You can prune the variable more efficiently, but you need to be able to compute this incrementally. And storing the variable that are not bound, you can use the sparse set data structure for that you can maintain yourself. So I will store, initially I've got all the variables here that are not bound, and the partial sum is equal to 0. I will scan the variable from the right to the left, starting from the current size. Okay? And the size here is the number of unbound variables. Okay? I start from the right, and I will go in that direction. As soon as I realize that I have my current variable which is bound, I will swap it. I will swap it with the last variable, but before that, I augment my partial sum. So I go in that direction. I realize that one variable is bound. In that case, you see that it took me n iteration to realize that it was the first one that was bound. I exchange it with the last one, like this, and I decrease the number of bound variables by 1, and now I've got this. If I continue like this, I will have x5 equal to 1, which is the next one which is bound. But now you see that I'm starting from here. So already I do the economy of one iteration on my array here. I realize that this one is bound. I swap it. I augment my partial sum. And my partial sum is now 9. Oh, sorry, it's now 5. Yeah, it's 5 because it's 4 plus 1. Like this. And the number of bound variables is now 8 because since I have already two variables that have been bound, this one and this one. The next one is x2 equal to 6. Again, you do the swap, you update the partial sum, and you've got this. And so you really have an incremental update of the two data structure, the number of bounds and the set of unbound variables. And when you will backtrack, they will just come back in your set. And so the big advantage of this is that you only have to worry when you go down in the search tree, but not when you backtrack. When you backtrack, the state is restored by the state manager, and so you don't have to worry about that.